Thank you. Okay, so thank you. Thanks all for being here. So my talk is on formal verification in scientific computing, and this is parts of these works, of the works I'm going to show, are collaborations with several PIs. So Karthik Duraisamy and I were in aerospace at the University of Michigan, and it's also collaboration with Andrew Appel that you just heard, just presented at Princeton, and David Bindel at Cornell. So why do we really care about correctness for scientific computing in the first place? You probably, most of you, maybe all of you know about this accident in '96 of the Ariane 5 rocket exploding because of a data conversion from a floating point to a signed integer value. And as Andrew just pointed out to me during the break, the program was actually correct just with the wrong specification. It was correct for Ariane 4, because Ariane 4 was not going as fast. But as soon as they put the same program that had worked for all these years on Ariane 4, on Ariane 5 was a bigger rocket, was going faster, and then they got an overflow, and then they lost the rocket. So that was too bad. And that was possibly the most expensive bug. Definitely, probably the most expensive bug for floating point. Another example, there are several examples I could pull, but another example more directly related to finite element approximation is the syncing of the Sleipner A offshore platform. And there was an inaccurate finite element approximation in some of the models, and basically they lost the platform. So that's also too bad. So to avoid these kinds of issues, we really want to verify that what we are simulating is actually correct. And maybe one of the moonshots, like the organizers talk about moonshots, is how to verify that something like climate change is correct, and in particular, how do we model the sheet of ice on, say, in Antarctica. So this is Antarctica, if you haven't recognized, and it's modeled the sheet of ice. And the problem with the sheet of ice is a little bit similar to the nuclear problem, but for different reasons, right? We cannot wait until for like thousands of years to see, or like even tens of years to see what happens. We have to simulate it and have an idea of what's going on. So this gives us a good idea of how it's a good place for me to remind everyone, or to explain how this process typically goes. So we have a differential equation. So we model the physics for the differential equation. And then this differential equation is typically discretized using a scheme, typically a finite difference scheme, or it could be a finite element scheme. And it's discretized into a finite difference equation. So the differential equation becomes a finite difference equation in a discretized scheme. Once we have this discretized scheme, we want to solve this discretized scheme. And this discretized scheme leads to an iterative solution. Usually cannot be solved directly, and so it leads to an iterative solution, which gives an approximate solution. And this iterative solution is also solved in floating point computation. And at many of these steps, we have errors. So we have an error here, we have an error here, we have an error here. And so all these errors accumulate to give a total error. And what we're interested in is to bound this total error to see, okay, how good is my approximation? Okay, so the questions we're asking is, how do we provide end-to-end mechanically checked guarantees for these algorithms? And programs, down to the program, down to the C program, or down to the other programs. Another question is, how can we generalize these methods so that the proofs that we do are not specific to just one single problem, but maybe apply more generally to computational physics? And a last thing is, maybe also this is kind of twisting the problem to convince my HPC friends who are always obsessed by performance, is to say, well, how can we use this mechanically checked bound information and error to guarantee the desired results using the lowest possible computational cost? And lowest possible computational cost means faster for HPC. Yeah. Okay. So let me get in the meat of things, and I really like to start with classifying the possible errors, a little bit like Andrew did, but maybe in a different way. And I really like this chart. Well, actually, it's just text, and we made it a chart that John Slater from NASA made a few years ago. So John Slater classifies the errors as in two different kinds. There's acknowledged errors and unacknowledged errors. And the first I'm going to talk about is unacknowledged errors, which is just computer programming errors. So like think about a bug, just like a computer bug. And on the other side, acknowledged errors, there are several kinds of errors. So there is discretization error. This is like when I go from my differential equation to my finite difference equation, a finite element equation, I have an error. I know I have an error. Iterative convergence error. So when we solve using iterative convergence, there's an error. Computer round-off error. This is where the floating point error comes in. And finally, physical approximation error. This is where my differential equation might not match the actual physics. And we're going to be able to help you with this, and this, and this. We cannot help you with final physical approximation error because if your differential equation in the first place is wrong, there's really not much that we can do. And these, and this is color-coded, and these will correspond to the three next parts of the talk. So let's start with discretization error, but first let's look at the process seen in a different way. So the same process that I described on the sheet of Antarctica looks like this. Okay, so initially, I have a differential equation which has an analytical solution u, and I write it IHU because it's just its projection in the discrete space, but just really think of it as u, the real value solution of the differential equation. Then the first computation step is to make it a discrete solution. Then to look for a discrete solution, then to look for an iterative solution, then a floating point solution, then I go to the C program, and then at the end, we compile the C program, and we get that. So what really we're looking for is u, but what we're getting is this UHN tilde. Okay, that's what we're getting. And then we can come back and see. So the first thing is, okay, we have a difference between u and UH, and the difference between u and UH, we want to be able to bound it, and we're going to bound it by an error EH. Then when we do iterative solution, we have again an error, EHN, and we can bound the difference between UH and UHN by this. When we do go floating point, from doing things in the reals to doing things in the floats, we add another error that we call EHN hat. Then when we go from the floating point to the C, here hopefully we don't have an error, and if we have an error we could bound it, but I just write here that we have equality, so we prove that the C semantics really matches what we want. And finally, we prove that when we want to prove that when the C program is compiled, we also get the same solution. And the final theorem we have is that under a bunch of assumptions to be specified, A1 through A5, the exact analytical solution that we're looking for and the binary solution that we are actually getting are not too far from each other, and we want to be able to bound this error. So this is kind of the grand vision of what we want to do. Okay, so this is really an end-to-end proof in the sense that we go from the analytical solution to all the way to the binary. Okay, so let's start with what can we do to bound the exact analytical solution versus the discrete solution. And to do that, and this is a collaboration with my student Mohit and my colleague Karthik, we proved formally the lax equivalence theorem. So the lax equivalence theorem is a classic result in computational science, so in numerical methods. And it says that if I have AU equals F be a differential equation, and AH, UH equals FH be its discretized counterpart for some discretization, and I call U the analytical solution, UH the numerical approximate solution. If I have two conditions that are true, so the first is called consistency, and consistency basically tells me that my discretization is correct in the sense that it's an accurate discretization. And that says that the limit of AU minus AH equals 0. We didn't discretize the wrong equation. And if it's stable, meaning this AH is the inverse of AH is bound by a certain K that is independent of H. If I have those two assumptions together, then I can prove convergence, and I can prove that the limit that U minus UH is equal 0. So we proved this. This first time we proved it was proved in a theorem prover using the calc theorem prover. And importantly, one thing that's important here is that this is a limit. So in a theorem prover, it involves kind of different kinds of techniques. And we went for the limit because the textbook gives us a limit, even though intuitively, maybe it's a little unsatisfying. I want like a hard bound. I don't want like a for all epsilon there is this eta, but we could accept. The Lax equivalence theorem gives you a limit. So just let me say a few words, because all the work I'm going to present, or have presented in this talk so far, are done in the Coq proof assistant. So let me just say a few words about the Coq proof assistant and theorem provers in general. So it's a formal interactive theorem prover and proof management system that has been started being developed in the early 90s, I think, late 80s. And it's a formal language to write mathematical definitions, theorems. And importantly, it's a system where you write the theorem, you write the proof, and then the system checks your proof for you, which is very useful for very intricate proof with lots of details where you have floating points. There are other proof assistants that are well known: Isabelle Hall, Lean, PVS, NewPerl, Agda. There are many more. Please don't be mad at me if I don't write your favorite proof assistant. And it's been used for several applications recently. The most prominent recently are the CompCert, so the Certified Compiler Project, came out in 2006. The Verified Software Toolchain by Andrew Appel and others for verification of C program. And then, so that's on the programming side. And then on the mathematics side, there are also proofs of big theorems like the odd order theorem or canonical big operators that have been formalized in Coq. It's just a little parenthesis. Okay, so let's go back to our chart of possible errors, and I want to look now at iterative convergence. So we've talked about discretization error. Now I want to talk about iterative convergence and how do we bound the error here. And in that process, it's getting this theorem that the discrete solution and the iterative solution are not too far from each other. Okay. So we have the first step we've done, okay, is that we had a differential equation. We get a defined difference equation. And once we have UH equals FH, okay, let's say, okay, now I can just invert AH and I get UH. The problem is that AH is like 100 by 100 or 500 by 500. It's a big matrix. And this big matrix, I cannot reasonably invert it efficiently. So that matrix inversion is expensive. And so what I do is that I'm going to use an iterative method. Typically, I'll go into more details, but I use an iterative method to get a sequence of values, UHM, such that UHM converges to UH. That's the idea. Okay? And this is a very old idea. I mean, the first person probably that's known that's used this, Gauss was already using it, maybe even people before him. So it's a very old idea, even though everything was done by hand. And so here on the left, we have that the difference between U and UH goes to 0. Here we have the iterative solution that goes to iterative solution error that goes to 0, and then we have the sum of the both goes to 0. So we wrote in Coq, and the statement is done for symptomatic iterative convergence. We wrote in Coq that, and we proved that UHM, so this sequence, converges to this UH. Okay, so this theorem here is for only if this matrix A1 inverse A2, its radius of convergence is less than 1. So this is a textbook theorem, and we proved it in Coq, and we specialized also this theorem to two. Well, I'll go into the next slide. Okay, and so in this, for this, we used several libraries. Especially, we used a mathcomp library for complex numbers definitions and linear algebra, and then we also used Coquelicot for expressing limits, which is another Coq library, which is progressively being replaced by mathcomp. But in this work, we used a little bit of Coquelicot. So in more details, what's iterative methods? It's saying, okay, I have a system AX equals B. I'm going to, and I want to find X, where A and B are known. And typically A also is sparse. That's another thing to consider. And what I'm going to do is I'm going to split the matrix A into two matrices, A1 and A2, such that A equals A1 plus A2, and A1 is easily invertible. A1 is easily invertible is key. Okay. And then I'm going to construct the system like this, A1xm plus A2xm minus 1 equals B. And rearranging, I get this sequence. And then I can start with an x0. Typically, we start with x0 equals 0, but theoretically, you can pick whatever you want. And then you compute the sequence of xm's, and the sequence of xm's leads to, like converges to X under the conditions I gave. So the most well-known at Jacobi is A1 is just a diagonal of A, okay? And Gauss-Seidel, which is easy to invert. And then Gauss-Seidel, where A1 is the lower triangular of A. And so in this work, we formalize the convergence of both iterative methods, and we have a general theorem. But here, I'll talk about the work we've done on Andrew later. This is not the work we've done with Andrew. This is done in the field of reals. Okay? So it's not looking at the C program directly. It's not looking at floating points. It's really formalizing the theorem like in the textbook. Okay? So it's not going down all the way down to the floats. Okay. So and so here we have the iterative matrix, and this is the iterative matrix that we want to. We want its radius of convergence to be less than 1. Okay, so we've seen discretization error, we've seen iterative convergence error. Now we want to talk about computer round-off error. Computer round-off error meaning floating point approximations. And at the same time, I'm also going to address computer programming error. And this is work, So computer round-off error and computer programming error. And this is, in this process, this corresponds to those two elements, right? The difference between iterative and floating point, and the difference between floating point and the C program. So we're going to address both of those together. So this is work, and this is the work that, part of the work that Andrew Appel just presented in his lightning talk. So if you see similarities, it's the same work. We're working on this together. And this is a collaboration with my student Mohit, Andrew, and David, who are here, and their student, and Arya Callison at Cornell. So here we're using the verified software toolchain principles, and so we're going to have a high-level property specification. We're going to write a functional model in the middle, and then we're going to have C code implementing the numerical algorithm. And so at the high level, we prove accuracy theorems about error bounds for a generic matrix A. And we assume, in one of the theorems, you assume there is an absence of overflow. And then in the other theorem, and we state precisely, and we prove in Coq, the precise conditions that we call Jacobi preconditions, so that we're sure there is no overflow. And on the other side, what we do at the refinement proof level, we write a simple implementation of the iterative algorithm. We write the functional model for the implementation, and we link it to the model to the top model. And then we write, we do the refinement proof from the C implementation to the functional model in VST. And all of this together gives us an end-to-end verification framework that goes all the way from the property specification, which was inverting this, like solving this AU equals AUH, AHUH equals B, to all the way to the C code. Okay. So just to give you an idea of what the C code looks like, so the top code is, so that's the C code we verify, part of the C code that we verify, the top level functions, I guess. So the first function is the one iteration of the Jacobi method of Jacobi. And so we see here that we use, this is a C method that's defined somewhere else that is used to perform matrix vector multiplication, and for which we have a lot of lemmas bounding the error when we do matrix vector multiplication. Those lemmas can be reused for other projects, of course. This is the definition of the residual, which is B minus AXK. And note here that we're using FMA, which is fuse multiplied add, which is used widely in scientific computing. And so for this work, we're doing the bounds with FMA. We actually started doing all the bounds without FMA, and then we realized, well, if everybody uses FMA, we should really use FMA. So all our bounds use FMA. And here so this is one iteration of Jacobi, so 1xm to xm plus 1, and this is like the full Jacobi iteration. And so we have, well, I'll show you the stopping criteria. And this criteria, we have a theorem that says basically that when we reach this criteria, this residual here is finite, and it's less than a certain tolerance. That's user specifies a certain tolerance tau, and we know that the stopping criteria knows that it's less than this tolerance. Okay, so Jacobi forward error. So what are the theorems that we prove? So just quickly, I'm not asking you to read the code, but just to give you an idea of what it looks like. So the forward error bound tells me that under some conditions, okay, these conditions here, the error is bound by a known quantity. That's what it tells me. Okay, so it guarantees that the forward error is bounded if we have no overflow, and then we have a set of conditions that we specify explicitly that are written in theorem prover. So like we check them and that there is no overflow. And what's important about those conditions that not only are they checked by the computer, so when you read them, I'm not going to show them to you, but there's 16, I think, different conditions, 17 maybe. So they feel like very like, okay, how can I be sure that things are right? But Coq tells you that things are right, so you don't have to worry about this. Mm-hmm. And the other important aspect is that those conditions are easily checkable. So I can check them. I can check them easily. Like I can run a program to check on a particular program, on a particular example. Those conditions are true. And it's maybe a couple pages of LaTeX, maybe 1 page of LaTeX. If you're doing it by hand, it's impressive, but for computer, it's really not that much. Okay, and on the way, we've developed a library for verified normalized error bound for matrix vector operations. That's also actually that's under submission right now. Okay, so this is what I showed you is like how do we talk about iterative solutions, like how do we do those two things to go from iterative solutions to C program solution. And actually I kind of lied to you a little bit. I lied to you a little bit because really what we do in this CICM work is that we do all of this. We really go from the discrete solution all the way to the C program solution. And before that I had gone from this to here. And basically we realized doing this work, and this is this is a lesson we're learning, is that even if you've done this work from going to discrete to iterative, it's difficult to link it with iterative to C program solution. Really, it's easier to just do all of this together. So we ended up, in this work, we end up doing all of this together. The previous work is still useful because the results are more general. Okay. So finally, I want to talk a little bit about this. So this is work we haven't done. And so how do we link the C program to the binary program? So this is, everything has to do with compilers, and there's been some talk about verifying the compilation. Of course, we're hoping to use something like ComCert, and we have good hope that things would go through relatively painlessly, although like this is famous last words. But so we have, we would like to extend the results to the binary program. But importantly, this would be a binary program that runs on a normal CPU. I think there's a lot of work to be done about, okay, so now what if it's running on a GPU? Like, what if it's running on much more complicated hardware? Where is this program in CUDA? And we don't have good answers to this, but I just want to point out that those are important questions. Okay, so this is the grand vision we have and what we're pursuing. And now I want to spend the last maybe 10 minutes talking about challenges and opportunities. And these are purposefully controversial, okay? And I feel like it is the kind of things we want in a workshop like this, to set out crazy ideas and see if people agree or disagree or what they think about it. Okay, so the first thing is, as a formal verification expert and collaborating with experts in scientific computing, we're proving. Is this blinking or okay? Is it bothering you? Or is it okay? It's okay. Okay, because I see it in the corner of my eye and I'm like, what's happening? Okay, cool. So discuss, and then I talk with Karthik a lot. So Karthik Duraisamy, who's my colleague at Michigan, and he's like, okay, so basically you prove this formal error bound, and it's basically 3 orders of magnitude off compared to what the experimental error is. It not always is, but this is a graph taken from a paper on the wave equation by Bordeaux and co-authors. And yeah, so basically the formal error bound that they proved is 3 orders of magnitude bigger than the experimental error that you get if you run things. And so, like, to put it bluntly, Karthik tells me this is useless for me. Like, if you give me a 3 orders of magnitude off, like, it's not really like a useful bound. Here's another example. So here is like for vector multiplication. We have a formal error bound that's around there. That's here, and then the experimental error is here, and we get about 2 orders of magnitude difference. between the theorem and what we get experimentally. A few other examples. So for Jacobi iteration, we run some numbers, and it's not as bad. So here, what we're looking at is the iteration count. So our theorem gives us a maximum. Here we're looking at the Jacobi iteration algorithm, and what is the forward error. And here we have about a 2x difference between what I see experimentally and what my formal error bound is. Okay, and we also have results on the number of iterations to converge, like a bound of the number of iteration, and the number of iterations to converge that we proved is usually about almost 2x, 1.6x what the experimental came in is. So if I run it until I get a small enough error, then if I know that k, I've proven a maximum k that I know that I'm going to like run less than say 30 times, and experimentally I run less than 15 or 20 times. That's what it is. Okay. So the question here is, are such theoretical bounds that are a little far off or really far off, like 2 orders of magnitude, are they useful for the computational scientist? And can the computational scientist do much with them? And what can we what can we do to offer tighter bounds? Okay, beyond of course trying to tighten better, trying to get better theorems, but at some point you reach a limit, right? And one way I like to think about it is that I think it's a reasonable model. I'm still thinking about it, but I think it's a reasonable model. Every time I do a floating point computation, it's like if I pick a number between +1 and -1. Okay, I basically have a random error, and maybe it's a little bit bold to say they're random and they're independent, but let's say it's like picking a number between +1 and -1 every time I do my error. Every time I do a floating point computation. And then my total error is the sum of all the numbers I got, right? Intuitively, and even you can do the computation, and it's very well studied. It's a random walk basically, and a random walk in one dimension. And so if I do 1,000 of this computation, there is a small probability that I'm going to get +1,000 or -1,000. But in practice, I'm only going to get stay between +30 and -30. And so that leads me to saying, okay, can we have probabilistic bounds that are, can we do probabilistic bounds where we get much tighter bounds, but only with probability maybe 90 or 95 or 99%, okay? So that's, and so I'm not the first to have this idea, and there's one paper actually that I encourage everybody to read. It's a really excellent paper by Nick Hyam and Theo Mary that looked into this, and they looked into this. Of course, they don't do formal verification, so all the proofs are done by hand, but still it's very interesting. So basically, they have some cases where, so the deterministic error bound will be here, okay, and this is log scale, remember? And they managed to get the probabilistic error bound, which is quite close to the experimental error, okay? So, and of course, I'm leaving a lot of details under the carpet here, but I really encourage you to look at this paper. And then another graph that they have, okay, so like the deterministic error bound will be in blue here, probabilistic error bound is in red, and then the experimental error is in yellow. And of course, see, in some cases, and here it happens where like the number of iteration is high, I think this is, then the experimental error goes above the probabilistic error bound, okay? But it gives much tighter bound. They managed to get this very, very tight. And that's at least discussing with Karthik, and I'd be really interested in seeing what the HPC experts think about this. It seems very, very attractive to have this. My counterpoint is like, what's the guarantee now, right? I'm in formal verification, and you tell me like I have a formal proof that it only works 95% of the cases. That seems very, dangerous, or like very, yeah. And like, yeah, so the question is like, is the probabilistic guarantee good enough, and for what use? And the counterpoint is also like in modeling, like there is a big error when you model. You assume, like Ignacio was saying, you assume that you have Newtonian mechanics, where we all know that Newtonian mechanics are an approximation. So there are already approximations that we ignore. So maybe it's okay to also approximate this. Anyway, I just want to launch a conversation on this. Okay, another challenge that I'd like to talk about is the formalization effort. So I haven't talked about, all the proofs that we've done are done in the Coq theorem prover, where there is some automation, but mostly you enter proofs by hand in a theorem prover. And for the lax equivalence theorem, we have about 14,000 lines of code. It was about 15 person month also, although a lot of it was my student who was learning, but still it was a significant effort. Iterative convergence was about 8 person month, and then the iterative convergence was about 5 person month. So it's a significant amount of effort for things that are specialized. Some results are general, but some results are specialized to one differential equation. And so the question is, how can we do things more automatically? And I'm in the camp, we do a lot of it using interactive proofs. I know a lot of you here are in the camp where we do more automatic proofs using different tools. And so the question is, the usual difference is that interactive proofs are more expressive, but require large amounts of manual effort. Automatic proofs are really attractive because they're automatic, but they're limited in expressivity, and when they get stuck, it's hard to know what to do. So I think it's important for us to think about where would be how can we use both together to get the best of both worlds. And I still want to argue that for complicated derivations, like say the lax theorem, the non-trivial bounds on derivations, I think that, and maybe ChatGPT will solve everything, but at least for now, I think that there are some non-trivial steps that will need some human input. And that leads me into my third challenge, and this is another crazy idea I have, is that I think everybody who is interactive theory improving knows that there is a very steep learning curve to a tool like Coq or Isabelle, PVS. It's very difficult. I mean, it's very steep. You really have to. First few months are always really hard. And that is really makes it really difficult for HPC experts to adopt those tools, because if there's a steep learning curve, they're like, okay, I've tried it for a week, I can't do anything, it's not useful for me. Okay? And so one thing that we've played with, and it's very, very early, is whether more familiar interfaces could help even in very specific cases. And we're thinking here about if you have a mathematical derivation, say an equality or an inequality, okay? Could I have a better interface that makes it really easy to get a Coq proof? And this was inspired by talking to my colleagues who do derivations by hand. And I asked them, do you use a computer? How do you do it? And I get various answers. Some people will say, I just do it by hand. Some people will say, well, I use a bit of Mathematica. I do a little bit of both. Some people will tell me, I do it. I get actually a lot of answers telling me I do it directly in LaTeX, because then I can copy paste. I can copy paste, and I know I'm going to, which I find crazy. I cannot do a derivation in LaTeX. And so there's just too many curly braces. I can't deal with it. But I have some colleagues, that's their answer. And so I'm thinking, okay, can we offer a tool? And here's the prototype of our tool that says, okay, I want to prove, and of course this could be automatized. This is a very small proof, so it would be easy to automate. But the idea is the tool. It's I can enter an expression. I want to prove that it's equal to this. And so I enter this expression. I just click on the plus, it reduces it. I click on the minus, it reduces it. I click on the multiplication, and it reduces it. I click on this, it reduces it. And then I can extract a proof that 1 plus 5 minus 3 plus a plus 3 times 5 plus 7 is equal to 3 plus a plus 22. Okay? This is a very simple example, and we have a prototype that does this right now. But you can imagine having this for much more complicated derivations with inequalities and equalities. And right now, it's quite painful to do those derivations in Coq. You have to do a lot of cuts and replace and everything, and it's very non-intuitive. And I think if we have a tool like this, we could really get the community to adopt it, I think. At least we could try. Okay, thanks. This is all I have. I want to thank my students and my colleagues, Mohit, who is graduating actually next week, and who's actually the week after? No, the week after. Well, I don't know. We're during the weekend. I never know what that means. But anyway, 10 days from now, Mohit is graduating, and he's on the job market. So he's led most of the work I've presented. So if you like this work and you want to hire a postdoc or somebody who can do this work, please let me know, and then I'll forward. And then Ariel, who's at Cornell, and then my colleagues Andrew, David, and Karthik at Princeton, Cornell, and Michigan, and then a few undergrads, Josh Miller and Ling Xiaoguan, who helped out. And thanks a lot to the NSF who's funded this work, and also and is organizing this workshop, and to the DOE who's organizing this workshop. Thank you. Thanks for your attention.
We have time for a few questions.
Sorry. I'll just quickly hand over to Kasia. There is a case study that we are looking at from Ichirato Yamazaki and Shiva Rajamanikam, which actually looks at termination. So they actually lower the precision, and sometimes they don't have termination. So Kasia, I want to say the GMRS thing that we are looking at. Yeah, anyway, that is the example that we played with. We can give you a pointer to that.
Okay, that would be great. Yeah.
First, thanks for that. That was a very thought-provoking talk. I just want to make sure I understood. Does your model problem assume that the continuous operator is linear? Yes. It does, right? Yeah. So have you thought of extending this to like one more outer loop, which linearizes over?
So, yeah, the problem with, well, we think about, so yes, we assume that everything's linear. And yes, we could, yeah, that would add another error. The problem is that when you go from nonlinear to linear, and I also have these conversations a lot with Karthik, but he's like, we can't do anything with linear. You need to handle nonlinear. The problem with going from nonlinear to linear is that there's often not a really good understanding how to bound the error. Like if I want to do that, as Andrew pointed out, I need you to give me a textbook that tells me how to bound the error from nonlinear to linear. And in many, not in all cases, there are cases where we can bound the error. But in most of the cases that are useful, the linearization is like, you do the linearization and you pray that it's close enough, right? I mean, at least that's my feeling. I'm not an expert, but I feel like from what I've seen. And if we want to be able to do formal proofs, I need to have a proof that it's not far enough. So if you have examples where nonlinear and linear are not far enough, provably not far enough, and we can formalize it, I would be really interested. But that's the main reason we haven't pursued that.
Okay, thank you very much.
Hey, thanks. Maybe a very different perspective, but in the hardware world, like regression tests and things like that are formal tools, and we will like spit these out, and we have experts in that sort of area providing templates and things like that. And as the designers, we're refining our designs, and we just make modified tweaks to these things. So is there some way this could kind of like, to go to your third point, maybe the experts are providing templates for these sort of problems, and not everyone has to be an expert, but we just have to understand how to like tweak these little things to make them work for our particular test case.
So basically, so let me just rephrase your question so I make sure I understand. So basically you say like, getting inspired from the hardware world, and if I have like a proof for a certain differential equation, I want something a little bit of a slightly different differential equation, and how can we adapt the proof? This kind of like what...
Yeah, and like regression testing as you're going along, but formal is just always there.
Yeah, so yes and no. I think that's, we could try that. I mean, we haven't tried that first. And I think it's not impossible. The problem with formal proofs that when they break, because you change something small, and even we see it sometimes because we have a new version of Coq, right? When they break, let's say 95% of the case, it's an easy fix. And there's this 5% where it's actually an involved fix. And so it's hard to predict how easy for a non-expert it will be to fix the proof. Sometimes there is a place in the proof that's just actually difficult to fix. Yeah, I don't know what else to say, but I think it's something that we could try, but in some way I'm a little skeptical because I feel like there's really probability that some crucial place in the proof is gonna break, and then it's gonna be really difficult to fix.